Hello friends, in the previous discussion we talked about simple harmonic motion which can serve as a mathematical model of a variety of motions. In today's discussion we shall be talking about a class of simple harmonic oscillators in which the springiness is associated with the gravitational force rather than with the elastic properties of a twisted wire or a compressed or stretched spring. The simple pendulum. Timing the oscillations of a pendulum has been used for centuries to measure time accurately. The simple pendulum is the idealized form that consists of a point mass m suspended from a massless rigid rod of length L as illustrated in this figure. For an angular displacement theta, the displacement of the mass along the arc of the circle of length L is L theta. Hence, the angular velocity along the arc is L d theta upon dt, and the angular acceleration is L d square theta upon dt square. At a displacement theta, there is a tangential force on the mass acting along the arc that is equal to minus mg sine of theta, where as usual the minus sign indicates that it is a restoring force. Hence, by Newton's law we obtain d square theta upon dt square is equal to minus g upon L sine of theta. This equation does not have the same form as the equation of simple harmonic, as we have sine theta on the right hand side instead of theta. However, we can expand the sine theta in a power series of theta as shown here. For small angular deflections, the second and higher terms are much smaller than the first term. For example, if theta is equal to zero point 0.1 radian, which is typical for a pendulum clock, then the second term is only 0.17% of the first term and the higher terms are much smaller still. We can see this directly by plotting the functions y is equal to sine theta and y is equal to 0 on the same set of axes as shown. The two curves are indistinguishable for value of theta below about 1/4 of a radian. Thus, for small values of theta, we need to retain only the first term in the expression in equation A and replace sine theta with theta to give d square theta upon dt square is equal to minus g upon L into theta. This is the equation of simple harmonic motion with omega is equal to under root of g upon L and t is equal to 2 pi into under root of L upon g, and we can immediately write down an expression for the angular displacement theta of the pendulum. Theta is equal to theta 0 into cos of omega t plus phi. Here, theta 0 is the angular amplitude of oscillation. The period is independent of amplitude for oscillations of small amplitude, and this is why the pendulum is so useful as an accurate timekeeper. The period does, however, depend on the acceleration due to the gravity, and so measuring the period of a pendulum provides a way of determining the value of g. In practice, real pendulums do not have their mass concentrated at a point. So, for an accurate determination of g, a more sophisticated pendulum has been developed called the compound pendulum. We finally note that for L is equal to 1 meter and for a value of g is equal to 9.87 meters per second square, the period of a simple pendulum is equal to t is equal to 2 pi under root of 1 upon 9.87, which comes out to be equal to 2 seconds. And indeed, the second was originally defined as equal to 1/2 the period of a 1 meter simple pendulum. The energy of a simple pendulum. We can also analyze the motion of a simple pendulum by considering its kinetic and potential energies. The geometry of a simple pendulum is shown in figure. The horizontal distance x is equal to L sine of theta is not exactly the same as the distance along the arc, which is equal to L theta. However, since sine theta is approximately equal to theta for small theta, the difference is negligible. From the geometry, we have L square is equal to L minus y whole squared plus x square, which gives 2Ly is equal to y square plus x square. For small displacements of the pendulum, that is x is very less than 1, it follows that y is very less than x, so that the term y square can be neglected and we can write y is equal to x square upon 2L. As the mass is displaced from its equilibrium position, its vertical height increases and it gains potential energy. This gain in potential energy is equal to mgy is equal to mgx square upon 2L. The total energy of the system E is given by the sum of the kinetic and potential energies, that is, E is equal to K plus U, which is equal to half mv square plus half mgx square upon L. At the turning point of the motion, when x equals a, the velocity v is 0, giving E is equal to half mg a square upon L. From conservation of energy, it follows that mg a square upon L is equal to mv square plus mg x square upon L is true for all times. We can use equation B to obtain expressions for velocity v and displacement x as v is equal to dx upon dt, which is equal to under root of g into a square minus x square divided by L. This expression describes how the velocity changes with the displacement x in simple harmonic motion. Since v is equal to dx upon dt, we have integral of dx upon under root of a square minus x square is equal to under root of g upon L into integral of dt. The integral on the left hand side can be evaluated using the substitution x is equal to a sine theta, giving sine inverse x upon a is equal to under root of g upon L into t plus phi. Here phi is the constant of integration and x is equal to a sine of under root of g upon L into t plus phi. Equation C describes simple harmonic motion with omega is equal to under root of g upon L and t is equal to 2 pi into under root of L upon g. At this point, we note the similarity in the expression for the total energy of the two examples of simple harmonic motion that we have considered. One we considered in the earlier lecture with mass on spring. For the mass on a spring, E is equal to half mv square plus half kx square. For the simple pendulum, E is equal to half mv square plus half mg upon L into x square. Both expressions have the form E is equal to half alpha v square plus half beta x square. Here alpha and beta are constants. It is a universal characteristic of a simple harmonic oscillators that their total energy can be written as the sum of two parts, one involving the velocity square and the other the displacement square, just as m d square x upon dt square is equal to minus kx is the signature of simple harmonic motion in terms of forces. Equations D are the signature of simple harmonic motion in terms of energies. If we obtain either of these equations in the analysis of a system, then we know we have simple harmonic motion. We stress that the equations are the same for all simple harmonic oscillators, only the labels for the physical quantities change. We do not need to repeat the analysis again. We can simply take over the results already obtained. The constant alpha corresponds to the inertia of the system through which it can store kinetic energy. The constant beta corresponds to the restoring force per unit displacement through which the system can store potential energy. When we differentiate the conservation of energy equation for simple harmonic motion with respect to time, we obtain dE upon dt is equal to alpha v into dV upon dt plus beta x into dx upon dt is equal to 0, giving d square x upon dt square is equal to minus beta upon alpha into x. The physical pendulum. In a physical pendulum, the mass is not concentrated at a point as in the simple pendulum, but is distributed over the whole body. It is thus more representative of a real pendulums. An example of a physical pendulum is shown in this figure. It consists of a uniform rod of length L that pivots about a horizontal axis at its upper end. This is a rotating system where the pendulum rotates about its point of suspension. For a rotating system, Newton's second law for linear systems m d square x upon dt square is equal to F becomes I d square theta upon dt square is equal to tau. Here I is the moment of inertia of the body about its axis of rotation and tau is the applied torque. The moment of inertia of a uniform rod of length L about an end is equal to 1 by 3 ml square and its center of mass is located at its midpoint. The resultant torque tau on the rod when it is displaced through an angle theta is given by the product of the torque arm and the component of the force normal to the torque arm, that is tau is equal to half L into minus mg sine of theta. Hence, we obtain 1 by 3 ml square into d square theta upon dt square is equal to minus half mgl sine of theta, giving d square theta upon dt square is equal to minus 3g upon 2l into sine of theta. Again, we can use the small angle approximation to obtain d square theta upon dt square is equal to minus 3g upon 2l into theta. This is simple harmonic motion with omega is equal to under root of 3g upon 2l and t is equal to 2 pi into under root of 2l upon 3g. In a simple model, we can describe the walking pace of a person in terms of a physical pendulum. We model the human leg as a solid rod that pivots from the hip. Furthermore, when we walk, we do so at a comfortable pace that coincides with the natural period of oscillation of the leg. If we assume a value of 0.8 meter for the length of the leg, then its natural period is approximately 1.5 second. One complete period of the swinging leg corresponds to 2 strides. Try this yourself. If the length of a stride is, say, 1 meter, then we would walk at a speed of approximately 2 divided by 1.5 meters per second, which corresponds to 4.8 kilometers per hour, which is in good agreement with reality. Small vibrations. A good example of simple harmonic motion in the microscopic world is provided by the vibrations of the atoms in a crystal. The forces between the atoms result in the regular lattice structure of the crystal. Furthermore, when an atom is slightly displaced from its equilibrium position, it is subject to a net restoring force. The shape of the resultant potential well approximates to a parabola for small amplitudes of vibrations. Thus, when the atoms vibrate, they do so with simple harmonic motion. Einstein used a simple harmonic oscillator model of a crystal to explain the observed variation of heat capacity with temperature. He assumed that the atoms were harmonic oscillators that vibrate independently of each other but with the same angular frequency, and he used a quantum mechanical description of these oscillators. As we have seen in classical mechanics, the energy of an oscillator is proportional to the square of the amplitude and can take any value, that is, the energy is continuous. A fundamental result of quantum mechanics is that the energy of a harmonic oscillator is quantized, that is, only a discrete set of energies is possible. Einstein's quantum model predicted that the specific heat of a crystal, such as diamond, goes to zero as the temperature of the crystal decreases, unlike the classical result that the specific heat is independent of temperature. Experiments show that the specific heat of diamond does indeed go to zero at low temperatures. Another example of simple harmonic motion in quantum physics is provided by the vibrations of the two nuclei of a hydrogen molecule. The solid curve in figure represents the potential energy U of the hydrogen molecule as a function of the separation R between the nuclei. When we have taken the potential energy to be zero at infinite separation, this potential energy is due to the Coulomb interaction of the electrons and nuclei and the quantum behavior of the electrons. The curve exhibits a minimum at r is equal to 0.74 into 10 raised power minus 10 meter. At small separation, the potential energy tends to infinity, representing the strong repulsion between the nuclei. The nuclei perform oscillations about the equilibrium separation. The dotted line in figure shows the parabolic form of the potential energy of a harmonic oscillator centered at the equilibrium separation R0. For small amplitudes of oscillation, that is, when the nuclei are not too highly excited, the vibrations occur within the range where the two curves coincide. Again, according to quantum mechanics, only a discrete set of vibrational energies is possible. For a simple harmonic oscillator with angular frequency omega, the only allowed values of the energy are half h bar omega, 3 by 2 h bar omega, 5 by 2 h bar omega, and so on. where h bar is Planck's constant divided by 2 pi. The observed vibrational line spectra of molecules correspond to transitions between these energy levels with the emission of electromagnetic radiation that typically lies in the infrared part of the electromagnetic spectrum. These spectra provide valuable information about the properties of the molecule, such as the strength of the molecular bond. Conclusion: a simple pendulum consists of a rod of negligible mass that pivots about its upper end with a particle attached at its lower end. If the rod swings through only small angles, its motion is approximately simple harmonic motion. A physical pendulum has a more complicated distribution of mass. For small angles of swinging, its motion is simple harmonic motion. Simple harmonic motion corresponds to the projection of uniform circular motion onto a diameter of the circle. So friends, here we come to the end of our discussion in this lecture. In the next lecture, we shall be discussing the damped simple harmonic motion. Thank you very much.